Okay, so I'm stopping the contest at this point. Like I could, the fourth is not accepted, but none of, no one has like got the fourth one. So I believe there's either something wrong in the author solution or the test cases. So anyway, I'll go through the problems. First one is check ASCII palindrome. So we are given a string S, and if we convert the string S into the binary string with the 8-bit representation of each character, then we have to check if the final string is a palindrome. So like in case this example ff, like f is 0 1 1 0 0 1 1 0, so it is already a like a palindrome like in itself. So the reverse of this will be matching for these two characters. So it will be like uh, let's say we have some characters, so each one of them will be having uh, yeah, some 8-bit representation, and each of them we have to concatenate this way, and then we have to check if they are palindrome in this way. So basically we are checking if the first character and the last character, like if like one is like the reverse bits of other. So if we just consider 4-bit integer, then the reverse of this is going to be 0 1 0 1. That's just we have to check, then it will be palindrome. So like in my implementation, I just converted the string into byte array. So this is like an unsigned 8-bit integer. So each will have its ASCII representation. I took the reverse, and then I compared each character, each uh, each character bit by bit, and then byte by byte, like each byte, each character I compared, and then I checked if one is equal to the reverse bits of the other one, as I explained. There nothing much to discuss here. Simple implementation idea. Yeah, problem B. So here we are given array and two integers lower and upper, and then we have to tell all the numbers which are not present, uh, like which are in the range lower to upper that are not in nums, and like the output can be large, so we are just asked to print a range from start to end. Like, I don't think it's that large. 10 power 5 should still work normally, but I think they wanted this in uh interval format. So it will also work for like if nums of I and lower upper are like 10 power 9 or something. So yeah. So let's if we see this example, we have to find all the numbers of 1 to 12 except 3, 9, and 7. So we have 1 to 2, 4 to 6, 8 to 8, and 10 to 12, skipping 3, 9, and 3, 7, and 9 respectively. So to implement this, it's basically the idea is first I like pushed upper plus 2 in the answer, because like I wanted like an upper bound to be present in the answer. Like if I will not do that, then I have to do some extra handling here. Like if in this case, if I sort the array, like I have sorted the array here, if I sort the array, then I'll get 3, 7, 9. Then for 10 to 12 I have to handle it outside the array. To not do that, I just added upper plus 2 in the array. Up plus 1 might also work. So yeah, and we declare answer. We start with the lower value, we iterate over it, and then this is the left bound of our current range, like a contiguous interval, and then we find a right bound, that is either x, or if we have already gone, or if we have some larger numbers than upper, let's say lower is 2, upper is 3, and we have a 5 here, so we will not consider that. So the right bound should be minimum of x, like the array no, element we are iterating over, and upper plus 1. So this is like an exclusive bound. Here it will be like L to R. R will be open. So here I check if there are elements in this range, then I add from L to R minus 1, and then I update L to R plus 1, because like R is a number which is there in the array, right? So we have to skip it. So we put R plus 1. So yeah, there can be simpler implementation, but this is like, I think, the most concise one. Like a little more ifs can make the idea simpler. But yeah, this is my second solution. Third one, longest subarray with at most k distinct prime factors. So yeah, it's the problem statement is self-explanatory. So we are given an array. We have to tell the largest subarray that uh, when we find a union of the prime factors, the count of unique prime factors is less than equal to k. So we can do this using binary search. We can do using two pointers. So I have done it using two pointers. If we just third one. So I use sieve to find the prime factors efficiently. So I'm not going to that detail. What is sieve? You can look it up. Sieve Ratosnins. So yeah, and I maintain a frequency map. This will be the frequency of the prime factors. So yeah, I run two pointers L and R, L inclusive, R exclusive. Then I iterate over while R is less than N and frequency is less than equal to K. So in this range, and then we like nums of R we have not included in our range, so we will add that in our range. So like for that we will add those add the prime factors of nums of R in our frequency mapping. So that is the idea. So we take some temporary x equal to nums of R, and while x is 1 greater than 1, we find its smallest prime factor and add it into frequency mapping. So like this will add all the prime factors of x together. Then uh, now one caveat of this is, if like I reach the end bound, like if r is equal to n, then uh, then this condition is satisfied, right? So in that case, L to R, so uh, it will be like this. It's a little tricky to explain, but if R is equal to n, then our answer will be of the range L to R. But if if currently our frequency dot length is greater than k, then the answer will be equal to L to R minus 1. Exclusive, that also exclusive. Because like I found it during implementation only, that the mapping, we need to be careful of that. We will add an extra value to the mapping, only then it will exceed this bound. So that extra number also we have to remove. So I have found the length this way only. If frequency of length is less than equal to k, if the condition is satisfied, then we take r minus l. Otherwise, we take r minus l minus 1. I hope that makes sense. Then we take the maximum of the length from what we have so far. And then similarly, like we have added r, we have removed l accordingly. Like if one small thing is, like if the frequency turns 0, we will remove it from the mapping to not count it. Like if any prime factor does not exist anymore. So yeah, so this is the third one. Fourth one, like I said, I couldn't solve, but I believe my idea is correct, if not implementation. But yeah, no one solved it, so I believe my solution is correct only. So yeah, so we are given an array nums, integer k, and some queries. So each query is a subarray. So for each subarray, we have to tell if it contains exactly k distinct numbers and the frequency of every number is even. And then you have to tell true or false otherwise for each query. So if you see this example 1 2 2 1, so 0 to 1, this will be false because we do have two numbers k equal to, like the frequency is 2. We contain exactly two distinct numbers, but like frequency of one is even, frequency of one is 1 and frequency of 2 is 1. So this second condition is not satisfied. For 0 to 3, both numbers have two frequency, so this condition is satisfied. So a way I have done it using Mohs algorithm, like I won't go too much into detail, but what it is, but yeah, uh, it's like we if we have some lot of queries L to R, and we will do it in an offline fashion. Like we need not solve the queries in the given order. We can just change the order of the queries to solve such that it becomes more efficient. So like let's say we have some numbers like this. So like I have taken 16 here. So what we can do is first of all we divide this into square root of n blocks. So I have taken 16 here, so it will be 4 blocks. So we divide it into square root of n blocks, and then we will sort the array or sort the queries on basis of first which block it like resides on. So let's say if this is our array and these are the blocks like 0, 1, 2, 3. So for each query we will tell which box it resides to, first of all which block. So let's say first query was from uh, 5 to 11, so it will reside in 0, 1, 2, 3, 4, 5. So it will reside in block 1. So first we will sort on that basis, then we will sort on the right bound, on the writer end, not on the block, on the value. So let's say I have some values. 5, 11 is fine. 6, 10. That will also be in B1, and 9 to 9, like a single range. Let's say. So 9 will be here. So this will be in B2. So if we sort this, we will get, first we will sort on basis of block. So B1 will come first, and then we will sort basis of the right bound, not the block. So the sorted array will be 6 to 10, 5 to 11, and 9 to 9. This will be the sorted queries. Now we will solve them in this order. So so the idea behind this is, like if we are at some value here, this is the left bound, this is the right bound, we have found a frequency for this range. Now what we can do is, if we want to find a frequency from here to here, we will just remove this one and this one to get here. So we will remove these two entries, and we will add some entries to the right. So on the right side, in the same block, we will always increase towards the right. In the left block, we can increase or decrease, but we remain in the same block. So the amortized time complexity of this entire thing will be n root n times the other operation cost. So of processing the queries, it will be n root n. So yeah, that is broadly the idea. So if we see the fourth one, first I store the frequency and odd count of odd numbers, like count of elements having odd frequency, and then I update. This just a simple function to update the frequency accordingly, frequency and the count of odd frequencies. Then I take b's number of blocks equal to square root of n, and then I sort the indexes. Basically for query, they are q queries. For each query, I will sort them on basis of first the block, then the right bound, block of the left bound, then the right bound. Then I store this, then take this answer array and this L and R as the range of the current range we are covering. Again, L inclusive, R exclusive. And then if you see the position we have sorted, this will contain 0 to Q in sorted order according to this. And that is the order we are iterating on. So answer of I also we are updating here. So that is not like 0 to N, 0 to Q. That is not the order we've sorted in. Then it's the simple idea. This is the query left and right bound given to us, right exclusive plus 1. Then while R is less than QR, I increase R and include r and then increase it. And while L is like greater than QL, so we have to go left in this. So we decrease L and include that one, that value, the previous value basically. And this case, like this case will only happen when we are switching blocks. So like we were in block 1, block 2. So we will go from 11 to 9. So the right value will decrease. So that this will not happen a lot of times. That is why our solution is decently efficient. And similarly here we are decreasing L, but this can happen multiple times. But this will not move a distance of square root of q times in the same block. Square root of n times in the same block. And then we just check our answer accordingly. So the time complexity of this will be n root n log n amortized. So that is the idea for fourth problem. I think it is correct, but I can't like prove it really because no one was able to submit the fourth problem. But yeah, that's it from my side. Thanks for watching. Bye.